Every single day, you use a piece of technology that only works because engineers corrected for time travel. Not theoretical time travel. Actual, measurable, happening right now time travel. We're breaking down every way time travel could actually work, starting with the one method that already does. Time dilation. Every time you open a Maps app, you're relying on GPS satellites that are literally traveling through time at a different speed than you are. And if nobody accounted for that, your position would drift by kilometers within days. Here's how it works. Two competing effects hit every GPS satellite in orbit. Because the satellites move so fast, their onboard clocks lose about 7 microseconds per day compared to clocks on the ground. That's special relativity. The faster you move through space, the slower you move through time. But there's a second effect pulling the opposite direction. The satellites orbit far above Earth, where gravity is weaker, and weaker gravity means time moves faster. That adds roughly 45 microseconds per day. Subtract 7, add 45, and satellite clocks gain 38 microseconds every single day compared to yours. That sounds tiny. It's not. Left uncorrected, that drift would destroy GPS accuracy within hours. So engineers bake the fix directly into the hardware, tuning each satellite's clock to 10.2999543 megahertz instead of the standard 10.23. The clock is deliberately built wrong on the ground, so it ticks correctly in orbit. But GPS isn't even the most dramatic proof. When cosmic rays slam into Earth's upper atmosphere, they produce muons, subatomic particles with a lifespan of just 2.2 microseconds. Barely any should survive long enough to reach the ground, but experimenters found them arriving at over 8 times the expected rate, because the muons were moving so close to the speed of light that time itself stretched for them. CERN later confirmed this with terrifying precision, matching Einstein's predictions to within 0.9 parts per thousand. This is the only entry on this entire list that's been proven, tested, and built into infrastructure orbiting your head right now. But if confirmed time travel sounds impressive, wait until you hear about the method that could theoretically let you skip across the universe in an instant. Wormholes. Here's the thing about wormholes. Everyone thinks they already understand them because they watched Interstellar or played through a Mass Effect relay. But the real science behind wormholes is way more interesting than any movie and way more terrifying. Wormholes aren't science fiction, they come directly from the same math that predicts black holes. The Schwarzschild metric, the exact set of equations that describes how black holes warp spacetime, also produces these tunnel-like structures, connecting two separate points in the universe. Einstein and Rosen identified them back in the 1930s. The math that correctly models every black hole we've ever observed also says these bridges should exist. But here's where it gets dark. The original Einstein-Rosen bridge is a death trap. The throat of the wormhole collapses so fast that nothing can pass through it, not even light. You wouldn't travel to another galaxy, you'd be swallowed by the singularity before you got halfway through. Every sci-fi movie that shows someone casually flying through a wormhole is skipping over the part where the tunnel crushes you out of existence. So how do you fix that? Kip Thorne showed that a wormhole could theoretically be made traversable if you prop the throat open with something called exotic matter, material with negative energy density that violates the null energy condition. Basically, you'd need a substance that doesn't just have zero mass, it has less than zero. Nothing like that has ever been observed anywhere in the universe. And even if exotic matter exists, the energy required to hold a wormhole open might be comparable to the total mass energy of the entire observable universe. Stephen Hawking made this worse in 1990 when he pointed out that the spacetime around any wormhole would need a saddle-shaped negative energy geometry, and that the whole structure would be catastrophically unstable. One wrong fluctuation, and it collapses into a singularity. But the time travel angle is what makes this truly wild. Certain wormhole configurations wouldn't just connect 2 points in space, they'd connect 2 points in time. Enter one mouth in 2025, exit the other in 1985. The math permits it. The physics just demands you break several other laws to make it work. And wormholes still require you to physically travel through something, but what if spacetime itself could loop you backward without any tunnel at all? Closed time-like curves. Every method on this list, the wormholes, the spinning cylinders, the cosmic strings, all of them are really just different ways of building the same thing. A closed, time-like curve. This is the mathematical shape that time travel actually takes inside Einstein's equations, and it's one of the most unsettling ideas in all of physics. Here's how it works. A closed time-like curve is a path through space-time that loops back on itself. You follow it forward, always moving into your own future, and you end up arriving at your own past. Think of it like a road that circles back to where you started, except instead of looping through space, it loops through time. You never hit reverse, you just keep driving forward and somehow end up behind yourself. The first person to stumble onto this was William Jacob von Stockham in 1937, who solved Einstein's equations for a rotating infinite cylinder and accidentally discovered these loops in the math. But nobody fully grasped what that meant until 1949, when Kurt Gödel, one of the greatest logicians who ever lived, found an entire universe where CTCs exist everywhere. Gödel didn't just suggest time travel was possible, he proved that Einstein's own equations allowed it. But here's where it gets deeply uncomfortable. CTCs don't just permit time travel, they break causality itself. An event can cause itself. No origin, no first domino. Just a loop with no beginning, feeding into its own existence forever. And that means the grandfather paradox hits harder here than anywhere else. Your world line loops back, you kill your grandfather, you erase yourself, which erases the trip, which means he lives, which means you exist again. A logical contradiction baked directly into the geometry of space-time. The cleanest escape comes from physicist Igor Novikov, whose self-consistency principle says something almost eerie. Any event on a CTC that would create a paradox has zero probability of happening, not unlikely. Zero. The universe itself enforces its own logic. Your gun jams. You trip. Something always intervenes because the math demands it. If all of this sounds abstract, that's because it is. CTCs are the theoretical backbone that every other method on this list is trying to build. But if you think bending space-time into a loop sounds impossible, wait until you hear about the scars the early universe may have left behind. That could do it naturally. Cosmic strings. Picture two scars in the fabric of reality, each one potentially stretching from one end of the observable universe to the other, flying past each other at nearly the speed of light. That's not science fiction, that's a real proposal for how time travel could work, and the math checks out perfectly. Cosmic strings are one-dimensional defects in space-time, left over from the earliest moments after the Big Bang. As the universe cooled from its initial superheated state, fundamental symmetries broke apart during phase transitions, kind of like cracks forming in ice as water freezes. Those cracks left behind these enormous, impossibly thin scars woven into the fabric of space itself. And before anyone confuses them with string theory, these are completely different things. String theory deals with unimaginably tiny vibrating filaments at the Planck scale. Cosmic strings are macroscopic objects. We're talking structures that could span the entire observable universe. But here's where it gets interesting. In 1991, Princeton physicist J. Richard Gott proposed something wild. He showed that if two infinite parallel cosmic strings passed each other at high enough velocity, the gravitational warping they generate would be so extreme that it would create closed time-like curves in the surrounding spacetime. Trace the right spiral path around those two strings at the right moment, and you'd loop back to where you started, except now it's the past. And this isn't hand-waving. Gott's solution is a legitimate exact solution to Einstein's field equations. The closed time-like curves it produces are mathematically identical in structure to the ones from Gödel's rotating universe model. The physics community took this seriously because the math gave them zero reason not to, but the universe apparently had other plans. That same year, a Physical Review Letters analysis dropped a devastating counterpoint. Researchers demonstrated that in an open universe, there is never enough mass available from decaying stationary particles to actually build this time machine. Worse, the entire mechanism cannot exist in any open universe with time-like total momentum, which describes the universe we actually live in. The math says yes. Reality says absolutely not. And even if you could somehow get around that energy problem, you'd still need to find two cosmic strings in the right configuration. Observations of the cosmic microwave background have increasingly tightened the constraints on how many cosmic strings could even exist, pushing the odds of stumbling across two parallel ones flying past each other at relativistic speeds into the territory of the absurd. It's the most elegant time machine that the universe refuses to let anyone build. But if you think an impossible cosmic coincidence is the only barrier to time travel, wait until you hear about a physicist who tried to solve the problem with brute force and a very, very large spinning cylinder. Tipler cylinder. Every other time, travel method we've talked about has the same annoying problem. You need exotic matter, negative energy, stuff that doesn't exist and might never exist. But in 1974, a physicist named Frank Tipler looked at the math and said, I don't need any of that. And on paper, he was right. Here's the recipe. Take about 10 solar masses of material, compress it into an insanely dense cylinder, and spin it at billions of revolutions per minute. The rotation creates something called frame dragging, where the cylinder's mass literally drags space-time along with it as it spins. Crank the rotation high enough and the light cones of everything near the cylinder start tilting. They tilt so far that part of them actually points backward along the time axis. A spacecraft spiraling around this thing in the right trajectory would find itself on a closed time-like curve, and according to Tipler's calculations, it could emerge billions of years in the past, potentially several galaxies away. But here's where it gets interesting. The math behind this wasn't even new. Cornel Lanczos found similar solutions back in 1924. Von Stockham found them again in 1936. Neither of them realized what they were looking at. Tipler was the first person to read those equations and go, wait, this is a time machine. He didn't invent the physics, he just recognized what it meant. And the selling point was huge. Unlike wormholes, unlike warp drives, unlike every other proposal on this list, Tipler's cylinder used only conventional positive energy matter. No exotic material required. Just regular mass, compressed and spinning. That's it. For decades, this made the Tipler cylinder the most realistic time machine in theoretical physics. But here's the part nobody talks about. Tipler's solution only works if the cylinder is infinitely long. Not really long, not astronomically long, infinitely long. Which is, to put it gently, a problem. Tipler himself suggested that a finite cylinder spinning fast enough might still produce closed time-like curves, but he never actually proved it. The core claim of his entire proposal was left unverified. And then Stephen Hawking showed up and closed the door. Hawking proved mathematically that building a finite time machine while satisfying the weak energy condition, meaning no exotic matter anywhere, is flat out impossible. His words were blunt. It can't be done with positive energy density everywhere. To build a finite time machine, you need negative energy. That single statement destroyed the Tipler cylinder's only advantage. The one proposal that didn't need exotic matter, turns out it only worked because it was infinitely long. Make it finite, make it buildable, and suddenly you need the exact same impossible material as everyone else. It's almost poetic. The universe gave physicists a time machine that runs on normal matter, then made it infinitely large so nobody could ever use it. But if you think a spinning cylinder bending spacetime sounds wild, wait until you see what happens when you bend spacetime into a bubble and ride it like a wave. Alcubierre drive. Most people hear warp drive and think Star Trek. Think spaceships zipping between star systems. Think science fiction. But here's the thing about the Alcubierre drive. The scary part isn't that it lets you travel faster than light. The scary part is that it lets you travel backward in time. And the math checks out. In 1994, physicist Miguel Alcubierre published a legitimate solution to Einstein's field equations that described something nobody expected to see in a serious physics paper. His proposal was elegant and terrifying in equal measure. Contract the fabric of spacetime in front of a ship. Expand it behind the ship. The result is a warp bubble, a pocket of perfectly flat spacetime that rides a wave of distorted space like cargo on a conveyor belt. The ship inside never actually moves. It just sits there, completely still relative to its local spacetime, while the bubble carries it across light years at apparent faster-than-light speeds. Passengers would feel zero acceleration, zero g-forces, nothing. You could hold a cup of coffee and not spill a drop of it while crossing the galaxy. But here's where it stops being a cool space travel concept and starts being a time travel concept. Under special relativity, faster than light travel and backward time travel are mathematically the same thing. If you send a signal faster than light in one reference frame, there exists another reference frame where that signal arrives before it was sent. That's not a thought experiment. That's a direct consequence of Lorentz transformations. A ship inside an Alcubierre bubble moving at superluminal speeds wouldn't just arrive at its destination sooner. In certain frames of reference, it would arrive before it left. And then reality hits you with the energy bill. Early estimates calculated that the exotic matter required to generate an Alcubierre bubble would need to carry negative energy equivalent to roughly negative 10 to the 64th power kilograms. To put that in perspective, the total mass energy of the entire observable universe is approximately 10 to the 53rd kilograms. So you'd need negative energy exceeding the mass of everything that exists by about 11 orders of magnitude. That's not a hard engineering problem. That's the universe laughing at you. But it gets worse. A 2009 analysis using quantum field theory found that at superluminal speeds, Hawking radiation inside the bubble would reach temperatures high enough to vaporize everything inside it, while simultaneously destabilizing the bubble itself. Your time machine melts its own passengers before it even works. However, and this is the part that keeps physicists interested, that problem completely disappears if the bubble stays below light speed. Recent work by physicists Alexei Bobrik and Gianni Martiri demonstrated that subliminal warp drive geometries could theoretically be constructed using only positive energy, no exotic matter required. A slow warp drive, one that doesn't break the light speed barrier, might actually be physically possible within known physics. The engineering challenges are still incomprehensible, but the theoretical door cracked open in a way nobody expected. So the Alcubierre drive sits in this frustrating middle ground. The version that enables time travel requires energy that doesn't exist in quantities that can't exist. The version that might actually work doesn't go fast enough to break causality. The universe seems to have built a very specific speed limit, and it enforces it with thermodynamics. But if warping space-time feels too large-scale for time travel, the quantum world might offer something far stranger and far smaller. Quantum time travel. Everything we've talked about so far operates in the world of Einstein, massive objects, curved space-time, exotic matter, but quantum mechanics doesn't play by those rules. And when you apply quantum theory to the problem of time travel, the results are genuinely unsettling. Not because they say time travel is impossible, because they suggest the version of time we experience might be an illusion layered on top of equations that don't care which direction they run. Here's where the floor drops out. In 1957, physicist Hugh Everett proposed the many worlds interpretation of quantum mechanics. The idea is deceptively simple. The universal wave function never collapses. When a quantum measurement happens, every possible outcome physically occurs, not metaphorically, not in some abstract mathematical sense. Each outcome branches into its own parallel universe, and the evolution of reality across all those branches remains completely deterministic. No randomness, no observer magic, just an endlessly splitting tree of equally real timelines. Now, apply that to time travel. In the many worlds framework, the grandfather paradox just evaporates. You travel back in time and kill your grandfather. Fine. You haven't erased yourself. You've created a branch where your grandfather is dead and you arrive from somewhere else. You're stranded in that alternate timeline with zero way back to your original one, but no paradox exists because causality holds perfectly within each individual branch. The universe doesn't need to stop you. It just routes around the contradiction. But here's where it gets genuinely weird. Two physicists took this quantum approach and built competing mathematical models for how time travel would actually work at the quantum level, and they reached very different conclusions. David Deutsch formalized quantum closed time-like curves in 1991. His model uses time evolution equations to show that only self-consistent quantum states survive interaction with a CTC. The chronology-violating region essentially filters out paradoxes before they happen. Think of it like the universe running every possible version of events simultaneously and only allowing the ones that don't contradict themselves. The constraints are invisible to classical reasoning, which is why nobody figured this out before quantum mechanics entered the picture. Seth Lloyd came at the same problem from a completely different angle. His PCTC model treats a closed time-like curve as a quantum communication channel using teleportation with post-selection. The final state gets post-selected to match the entangled initial state, which mathematically enforces self-consistency through projection rather than constraint. The difference matters. In Lloyd's model, a time traveler could kill their grandfather in one branch and remain alive in another. The many worlds branching structure absorbs the paradox entirely rather than preventing it through Novikov-style cosmic enforcement. So the question becomes, do paradoxes get prevented, or do they just get exported to a parallel universe where someone else deals with the consequences? Neither model has been experimentally tested. Neither model can be with current technology. But both are built on real mathematics, and both point to something deeply uncomfortable about the nature of time itself. The Schrödinger equation, the foundational equation of quantum mechanics, is completely time-symmetric. It runs equally well forward and backward. There's nothing in the math that says time has to flow in one direction. The arrow of time we experience, the feeling that yesterday is fixed and tomorrow is open, that's not built into the physics. It's imposed on top of it, likely by entropy and thermodynamics rather than by anything fundamental to reality's source code, which means at the deepest level physics can currently probe, the past and the future might be far more interchangeable than our brains are wired to accept. But if quantum mechanics hints that time's direction is optional, there's one approach that takes that idea to its logical extreme, and it doesn't require wormholes, exotic matter, or parallel universes at all. Retrocausality. Every other method we've talked about today requires something extraordinary. A spinning cylinder the size of a solar system, exotic matter that probably doesn't exist, wormholes held open by negative energy. But retrocausality doesn't need any of that. It proposes something far more unsettling. That causation itself might not work the way you think it does. That the future can reach back and influence the past. And that this might already be happening in every quantum interaction, everywhere, all the time. Here's how it works. When you measure a quantum particle, that measurement changes its state. That's standard physics, nothing controversial. But Rod Sutherland at the University of Sydney noticed something hiding inside Heisenberg's uncertainty principle. The uncertainty principle is time-symmetric. There's no mathematical reason that the influence of a measurement can only flow forward. It can flow backward, too. Sutherland built the first formal mathematical model integrating retrocausality into broader physics, and the implications are staggering. Think about quantum entanglement. You measure one particle and its partner instantly knows the result, no matter how far apart they are. Einstein hated this. He called it spooky action at a distance because it seemed to violate his own laws. Nothing is supposed to communicate faster than light. But here's where retrocausality flips the entire problem on its head. What if the particles aren't communicating faster than light at all? What if the measurement sends its influence backward through time, so the correlation was established before you ever looked? No faster than light signaling required. Einstein's locality principle stays intact. Sutherland himself claimed his model is the first to demonstrate that quantum mechanics and special relativity can be fully compatible when retrocausality is included, that entangled particles reside in ordinary space and obey Einstein's laws of relativity despite appearing otherwise. But here's the part that will keep you up at night. The Wheeler delayed choice experiment. A single photon is fired through an apparatus, and the experimenter decides at the very last possible moment what to measure, wave behavior or particle behavior. The photon's earlier behavior, what it did before the choice was made, appears to change based on that future decision. The universe seemingly rewrites what already happened based on what you choose to do next. That sounds like definitive proof. Except it might not be. In 2024, physicists Weiser and von Neervin published a careful step-by-step analysis of these exact experiments. Their conclusion was that every result attributed to retrocausality can be fully explained by standard quantum correlations and conditional probabilities. When you properly track the entire entangled system instead of looking at isolated pieces, the apparent information from the future dissolves completely. The math still works with retrocausality included. It just isn't required. And that's the question nobody can answer yet. Retrocausality isn't wrong. It's a mathematically valid interpretation of quantum mechanics that elegantly solves problems physicists have argued about for a century, but it might also just be a different way of doing the same math, a reinterpretation rather than a discovery about how reality actually operates. So we're left with this, not a machine, not a wormhole, Not exotic matter or spinning cylinders, just the possibility that every quantum measurement you've ever been a part of, every photon that's ever hit your eye, was shaped by events that haven't happened yet. And we genuinely don't know if that's real or if it's the most elegant illusion in all of physics. If you enjoyed this video and want to see more, click the video on the screen now.